if the agent experiences certain states and tries different actions in these states, then it wants to extrapolate into similar states, and so as to know how to act, how to act in the best way in these other states as well, which has not experienced. And the other important thing is about transferring decision-making knowledge between tasks, because as humans, we learn how to behave and execute a certain task, but then we can use this knowledge in order to perform other tasks as well, quite easily. Similar tasks, or in some cases not so similar. This is not very easy for reinforcement learning agents, and this is an active field of research in this field. And the other thing, the fourth thing, is consequences and rewards. So, as I said, the agent in every execution of this basic loop gets a reward. This is not the case in any setting. Okay? The agent may get rewards very infrequently, or it may get a reward at the very end, while reaching the target state. For instance, when a robotic arm, as I said, prepares and boils an egg, then it gets a reward at the very end. Okay, where you taste the egg. If it's good, then you get a high reward. If it's bad, you take a bad reward. But then, what you have to do, what the agent has to do is to go back and provide some credit assignment to its decisions back in time in order to see what were the decisions that affected this outcome, either good or bad outcome. So, in order to learn again and correct its policy if needed. So these are important things in reinforcement learning. So why deep reinforcement learning is important? First of all, due to generalization abilities. Okay, in classical reinforcement learning, as we said, in tabular reinforcement learning, you cannot deal with a huge state action space. Okay? So you need something more. And here is what deep technology goes in. And in order to have the generalization abilities, and also what you also have is the end-to-end training abilities. So in standard RL, what you do is what you do also in standard machine learning task, classical machine learning task. You engineer the future. Here in RL, you also have to shape the reward function and let the agent learn the best policy. But in deep reinforcement learning, you have a large deep network where it allows the agent to select on its own the best features and learn in an end-to-end way the best policy. What this involves? Two major stages. The first stage is perception, and the second stage is action. So in the first stage, the agent takes perceptions of the world through its sensors, for example, a camera, and gathers information on states. Let's call this information observations. I will make a distinction between states and observations later on, but let's consider that it takes some observations through its sensory equipment, and then feeds this observation to a neural network, which implements the policy. Okay, and this provides in the output the probability distribution over actions. If you have a stochastic policy, and the agent applies this policy and this action to the real world, and so on and so forth. Advances in deep RL go in par with advances in deep learning. Okay, some further notation. So we have states and observations. You have also the reward at every time step, observations OT, rewards RT, and you have here the network, the policy network, let's call it pi theta, where theta are the parameters of the network. Okay, and this network provides the probability distribution over actions AT given observations of agent OT. In case the agent can have full information of the state, then we have a fully observable setting. So the decision and actions are conditioned into the states. But in partially observable setting, which is the most usual setting, case of settings, the agent gets a decision and actions given only observations, OT, from the environment. What's the distinction between states and observations? Imagine you drive your car and you have full visibility, 360 degrees visibility in a long horizon in the road. You have, let's consider that is the full information you have from the state of the environment. But then you have a huge truck in front of you and a huge truck behind you. So you don't have full observation. You don't have the full information of the environment. You can have some observations of the environment. Okay, so this is the distinction between the state and observation. And having a partially observable setting is due either to, because the agent cannot have the perfect sensory equipment, or because the environment does not allow the agent to sense the full state information. Okay. And here you can see how things proceed with this graph. So the agent is in a state. Let's consider this to be an initial state. And then it perceives some observations from the environment. Based on these observations, it decides, using the policy pi theta, on the action that it will apply, and based on this action and this state, the environment proceeds to the next state, given the transition probabilities PST plus 1 given ST and AT. So ST plus 1 is the next state, given that the agent is in state ST, and it applies AT. Of course, the environment knows the state. The agent gets some observations from the state. So the agent applies actions according to the policy, and the environment decides the transition to the next state, given actions and states in this setting. So the story proceeds in the same way for the next stage, and here you have the Markov property, which means that the state ST plus 1 is independent from the state S minus ST minus 1 given ST. So S3 is independent of S1 given S2. This is the Markovian property, but consider that you don't have the Markovian property if you have a partial observable setting. So you may need the full history of observations in order the agent may need the full history of observations in order to reach a decision. Okay, so having this model, the agent constructs the trajectory in any case, starts from the first state, gets some observations, applies an action, gets a reward, and the environment lands it to the next state, S2, given its own model, its own transition probabilities. The agent gathers new observations, applies new actions, gets new reward, and so on until the end of the trajectory, until reaching the end of the task, the target state, or forever if it is it's a whole living task. So the agent gathers these rewards, and by summing, and the goal of the agent, as I will say in a minute, is to gather the maximum sum of rewards along the trajectory in expectation. Okay, so what's the probability of any such trajectory under this model? Let's call it trajectory tau. So the probability of such a trajectory given a policy pi theta is the product of these things. First, the probability of choosing the first action, then the probability of applying a certain action at any state t from T1 to capital T, a product with the probability of transitioning to the next state, ST plus 1 given ST and AT. So it's a product of probabilities. You can also add here the probability of getting certain observations. Here I assume a fully observable setting in order to simplify things. And the objective of the agent, as we said, is to learn the best policy. So the aim of the agent here is to tune these theta parameters, which are the parameters of the neural network modeling the policy of the agent, in order to get the maximum expectation over trajectories sampled from this distribution of trajectories, the expectation of the sum of the rewards that the agent gathers along the trajectory. Okay? So the agent wants to get the maximum reward along the sum of rewards along the trajectory, an expectation. By an expectation, because you have a stochastic policy and because the environment is also stochastic. Okay, some more definitions in order to proceed. The first definition, these are definitions about value functions. And value functions allow us to evaluate actions, the value of actions at specific states, as well as the value of states. Okay, so here you have the Q value function, Q over states and actions, which is equal to the reward that the agent gets when applies action AT to state ST, plus the reward that accumulates until the end of the task, while acting according to the policy. So the important thing here to understand is that this action applied to the first state, ST, is not the action, let's say, provided by the policy. So the agent here applies an action and wants to evaluate that action in that state, independent of what the policy dictates, let's say, for that state. But then, if it applies that action, then continues from the next state, ST plus 1, according to the policy, and gathers all the rewards according to the policy. Okay? And the value of a state, V over ST, is equal to the, expected sum of rewards that the agent gets along the trajectory starting from the state ST, acting according to the policy. So the difference between V and Q is that the agent starts from the state ST and applies the policy, while here the agent applies in ST and any action, AT, and then continues according to the policy. So V here can be considered to provide an average value over actions, because what you can see here, the V is an expectation over Q values, the action of the values of actions, of different actions, sampled from the policy in the state ST. So it provides an average, the average value of all actions. So if you have the case where you have an action which has a larger value than the average, then the agent should consider that this is a good action and should modify the policy and increase the probability of that action. So this is a comparison of the value of an action over the average value of all actions. And this, let's say, measure is provided by what is called advantage. And the advantage function is exactly this. It's simply the difference between the Q value of a specific action from the average. Okay? So higher advantage means that you have an action that is better than the average in a specific state. And finally, you have the Bellman backup, which shows how we can update Q values. The Q values according to a policy of actions in specific states is equal to the reward that the agent gets while applying that action in that state, plus the expected value of the next state. Why the expected value? Because the environment is stochastic, so the next state depends on the model of the environment. So you may have different next states with different probabilities. Okay, what's the anatomy of a deep reinforcement learning algorithm? This is a very nice, let's say, way to show, in general, the general structure of deep reinforcement learning algorithms. So imagine you have a random initial policy. Of course, the agent needs to learn the best policy, but let's imagine that it starts from any random policy and runs that policy in the environment. So it applies actions according to that policy, gathers samples, that is interactions, and using these interactions, it builds a model. Okay, it's a model. What's that model? Well, there are different choices for that model. I will explain that in a moment. But let's consider it fits such a model, and then uses that model in order to improve the policy. And by improving this policy, it has a new version of the policy, improved, and applies this policy to the environment. It gets a new set of samples, a new set of experience that it uses also to continue fit the model, improve the policy, and so on and so forth until it converges, or until it gets to a point where it has a very good policy for behaving. Okay? So this is the basic structure, and let me show you some examples. Here we have, for instance, value-based algorithms, where in that case the model is the value function, either the value of a state or the values of actions in states, so either V or Q, as said before, and you can construct based on that. So here, for instance, you can have a neural network that takes and input states and actions and predicts the value of these things. For the policy according to the samples, and you can improve the policy by setting the policy at the state S equal to the best action. That is the action that maximizes the expected reward that the agent is going to get until the end of the task. So the best action, the action with the best value. So these are value-based algorithms, or you may have Q-learning algorithms, where you fit either V or Q again, but here you fit Q, so you can update, here you have the neural network for Q values. You can update this neural network using here the usual temporal difference, the usual Q update rule according to Bellman. And you can also, as I said before, and also you can have an estimation of value of states, which is equal to the max Q over actions that can be applied at any specific case. And then again, you can use these models in order to set again to get a deterministic policy for at any state, which is equal to the best action at that state. Okay. Another kind of algorithms is the direct policy gradient algorithms, where the agent sums the rewards, executes the policy, okay, again, samples trajectories, and sums the rewards that it gets along these trajectories. It may get a large number of trajectories, let's consider n trajectories, and and gets the sum of these rewards for all the trajectories and the average of these, so divided by n, by the number of trajectories. So this is the empirical expectation that the agent gets to a number of trajectories, and then it can use that doing gradient descent steps in order to improve the policy. We will return to these algorithms. And another type of algorithms are the actor-critic algorithms, which combine previous types of algorithms. You have a model of value functions here, but here, instead of taking the gradient descent step over the accumulated rewards gathered along the trajectories, here you have the gradient descent over the value model that you have here. So you have the grad theta on Q values, or the Q value network. and you update the policy in that way. So these are different kinds of algorithms, and there is another kind of algorithm that I do not have here, which are the model-based algorithms. So in this case, here in the model, you have the model of the environment. So the agent wants to predict the transition probabilities of the environment, so how the environment transits from state to state while the agent applies actions, and then it exploits these probabilities, either simulating the environment or planning in order to fit a better policy. So these are different kinds of algorithms. So where's that? Okay. I'm going to skip that. So what I have presented so far is the motivation for deep reinforcement learning, some notation definitions, a specification of the deep reinforcement learning objective, and the anatomy of deep reinforcement learning algorithms. So, the second part, I'm going to continue on a very important question, and I say quite important question, because why is it important? Because it gives us a very good background on understanding some very widely used algorithms, and also gives us a very nice background on continuing other things such as imitation learning and inverse reinforcement learning, where the agent does not learn by interacting with the real world, but it learns getting samples of interaction provided by another expert agent. So it learns by demonstration, as we say. By exploiting a played data set. You can see that in the literature. So the important question here is that in many cases, or let me start differently. As we said before, the aim of the agent is to learn the best policy, okay, the optimal policy, P star. So the agent learns to act in the best possible way, in the optimal way, in any case, in any state. However, this is not the case for any human being behaving. For instance, for us humans, we may behave quite optimally when we are in a very, let's say, safety critical situation or in a very strategic moment while performing a task. But in some more relaxed cases, we may not be that optimal. Okay, so we may provide different kinds of actions, also due to mood or due to the level of attention that we pay, and so on and so forth. So we may demonstrate suboptimal or stochastic or random behavior in some cases. This does not mean that we don't aim to behave in an optimal way in expectation, in the average. But it just says that we may act in a suboptimal way or in a random way in some cases. Okay, so the question here is, can we reveal rationality and recover rationality to take into account randomness and stochasticity of behavior? Okay, and in order to answer that question, in a very nice article, Sergey Levin in 2018, RL and control as probabilistic inference proposed that setting, where it, in the usual graph that we had before, it also adds some optimization variables. Script 01. So these are not observations as before. These are optimization variables. So these are binary variables. Are 1 when the agent acts in an optimal way, 0 when the agent does not act in the optimal way. And you can see also the difference in the probabilistic graph here, where this one depends on the state and the action at any specific time point. Okay. The other things are as usual. The agent provides the action according to the policy. The environment transits to the next state according to its own model, and so on and so forth. By using that model, let's specify that the probability of acting optimally at any time step t, given you are in a state st and you apply action at, is exponential to the reward of st and at. This is reasonable, because if you get high reward, that means that the action is very good. So the probability of acting optimally should be increased, and this increases exponential to the reward that you get. And when the action that you apply is not that good, you get a very low reward, and again, the probability of acting optimally should increase also exponentially. Okay, there's an assumption here that rewards are positive numbers. This is not without without losing generality, and you can recover in any case. I leave it as an exercise. So, what's the probability of any trajectory when acting optimally throughout the trajectory from the first state to the last state, capital T? At time point, capital T. Without delving into details, it's very easy to figure out. It's proportional to the probability of the trajectory, as said before, according to the policy and according to the model of the environment. Product to the exponential to the sum of the rewards. So again, in cases with low reward, are exponential are less likely to be chosen. So again, here trajectories with very low accumulated reward have low probability under the conditions that you act optimally throughout the trajectory, quite reasonably. Okay, what you can do with this model? This is the interesting stuff. Okay, so here what you can do is you can calculate you can compute the policy. How you can compute the policy? With message passing. The usual message passing thing that you use in other kind of graphical models. So you can have backward and forward messages. I'm not going to delve much into the detail of that. But I'm going to show you some things. So you can compute the policy AT given ST as a ratio of backward messages. Backward messages vita from ST AT. Ratio to backward messages on states, ST, multiplied by a constant number. What is the constant number here? Is action prior, assuming a uniform distribution. Nothing important, but the important thing here is that you can compute backward messages for states and actions and states, and taking this ratio for the backward message, you can compute the policy. This is very important because it drives us to something quite important. So what are these backward messages? Just to show you the shape of these messages. Of course, backward messages starts from T -1 and proceeds according to the first state, backwards case. So for messages on states and actions, it is equal to the probability of acting optimally at any state ST and action AT, multiplied by the expectation given the state probabilities of the value according to the backward messages to the next state. This is very similar to the Q value I defined before. And there's a connection. I will show you that in the next slide. And also, backward messages on states are equal to the value to the expectation over actions sampled from the prior on values on state and actions, backward messages on states and actions. Quite similar also to the V value to function over states that I defined before. And there's also a connection on that. Okay, so given these ways to compute backward messages, let's define the Q now value equal to the log of vita over states and actions, which is equal to the reward that agent gets when applying an action at the action AT at state ST, plus the log of expectation of exponential to the values of next states. This is very similar to the Bellman update, but it has a very strange thing here. We will comment on that after defining V. So the value of states is equal to the log of backward messages on states, which is equal to the log integral exponent to the Q values of ST and AT over actions. So there are two important things to note here. The first is that this update on Q values implies an optimistic transition. Why an optimistic transition? Because here you have a log of sum, in case you have a discrete setting. Let's say you have a sum in the general setting and expectation, the log of sum of exponents over the values of next states. So if you are very lucky and you have a state which has a very large value, but it's very infrequent, it's not very probable, this log of exponents is dominated by this large value, by this very improbable state of very high value. So this is an optimistic bias to the estimation of Q values. Okay? And here you have a softmax in the definition of V. Why a softmax? Because here again you have a domination of large Q values. So it's not the usual softmax we have in neural networks when computing probability distributions, but you have a softmax kind of thing on Q values. Okay, so by having these definitions, we can reveal this interesting case where the probability of an action over a state is exponent to the advantage. Okay, what it says here, it's very again reasonable. Where you have an action that has a high advantage, which means that is much better, or it's better than the average of actions in a specific state ST, then the probability of that action increases according to the exponent of this average for that action. Quite reasonable. So, what does leads? This leads to soft algorithms. So you have we have soft Q learning algorithms where you can update the Q values using this update rule with an optimistic bias, and you can calculate the values of states using the softmax equation. And also you can improve the policy by setting the probability of any action equal to the exponent to the advantage. High advantage, high probability. Low advantage, low probability, exponentially. Okay, so if we do some calculations, and because I don't have time, if you do the calculations and you do some kind of variational inference, then we have two interesting things continuing. The first thing is that you can recover the regular Bellman backup, so you don't have this optimistic variable on Q values, as I said before. And the other important thing is that you change a bit the objective of the RL. So the objective of the RL was to maximize the reward. But here you can add something more to the objective. It's to maximize the reward and also the action entropy. So yeah, you can maximize the reward, but you can also act somehow randomly in some cases. This is the main idea here. In this kind of thing, we may have the soft Q learning, where you update the Q learning according to the usual Bellman backup rule without the optimistic bias we had before. You can also calculate the value of states, and you can have, again, the probability of actions given this in the exponent to the advantage. A very widely used algorithm, which is based on these ideas, is the soft actor critic algorithm, proposed by Harnoza et al. 2018, where you have the update of Q values as usual, but also taking into account the entropy of actions. This is the red part here. And you can also update and improve the policy, taking into account the Q values using this KL divergence measure. And this results into this objective where you want to minimize the minus of Q values and minus of entropy, which means that you want to maximize Q values and entropy of the policy. So again, high reward. This is the objective, high reward and high entropy. Okay, I'm going to close here. There was another part on another kinds of algorithms. It may not be that interesting, but it's better to stop here and also have some questions. There are many other interesting things on reinforcement learning. For instance, you may have offline reinforcement learning or goal-conditioned reinforcement learning. You also may have reinforcement learning with human feedback, which is something that is applied for tuning LLMs, the answers of LLMs. You can also have, as I said before, inverse reinforcement learning, as well as imitation learning involving also reinforcement learning in some cases. So there are many interesting other things that you can explore. So thank you very much, and I hope that I gave you some ideas in order to maybe continue studying on this interesting topic. Thank you very much.
My personal experience with reinforcement learning is that it works or it doesn't work, provided you find the right states and the right actions and the right rewards. And so one question is, if you have some ideas, given a particular physical system, how does one go about identifying state actions? Do you use domain knowledge? Are there automated ways or mathematical ways of finding optimal states and optimal actions?
I don't know if there exist optimal states and optimal actions, but of course you have to have a good grasp, let's say, of domain knowledge. So you have to explore a lot of the state action space, which means that you have to think a lot so as to formulate the problem and give a representation of states and actions so as to allow the agent to explore effectively, first of all, this is very, very critical, and also to have a way to generalize over actions that it has not experienced during training. So having a very good representation of states and actions is very critical and needs considerable study before starting, playing with the algorithms and so on. Yeah.
Other questions? Please.
Hello, thank you for the presentations. I would like to ask you, do the agents cooperate? For instance, you have aircrafts approaching an airport or cars approaching a gas stations.
Yeah.
Do they cooperate? And another question?
What I presented, this is a very good question, thank you very much. What I presented is a single agent, is a single reinforcement learning agent setting. But there are many other cases where you have multiple agents which may cooperate or maybe antagonistic agents, maybe adversarials. In my slide deck, which I will share with you, I also have a part with multi-agent reinforcement learning, so you can have certain ideas on that, on multiple agents with reinforcement learning and how we implement. This is an ongoing research field. The main problem there is scalability. You cannot have too many agents, more than 10 or 12, for instance, in the best case. But you can have some ways to go ahead. For instance, we have applied independent learners, multi-agent learners in more than 7,000 agents, in a setting with more than 7,000 agents. This is a very large setting. There are many interesting things to explore there for multi-agent reinforcement learning. Thank you for your question. Yes.
And one more question. What happens in case of emergency? When you have an aircraft in an emergency or a car catching fire suddenly?
What do you mean by emergency? Emergency situations?
Yes, in emergency situations, when an aircraft has a depressurization problem or a car catching fire in front of you.
Well, this is a difficult question. If you mean safety critical states, if you mean that, this is a difficult question. And there is also another branch of reinforcement learning research which considers safe reinforcement learning. This considers how to act so as to maintain, in every case, even when you are learning, when the agent learns, to maintain safety in any case. So this is also another interesting field of safe reinforcement learning.
Thank you.
Thank you.
Other questions? There's one up there.
Thank you. I would like to ask, because the whole setup reminds me a lot of control theory, in fact. Could we have also, in our reinforcement learning setup, controllers that correct the actions of the agent, for example, and instead of having the agent to run a lot of actions, to have the controller that
there are some works doing that in reinforcement learning. As I said before, in safe reinforcement learning, you want to clip or you want to forbid actions which are not safe. There are such works in the literature, yeah.
Okay.
Are not the most successful, I would say, but there are some, as far as I know.
Supervised learning, like neural nets, and is there a hybridization of the two? You alluded to that, I believe, but maybe you can say a few more things.
Yeah, okay. Of course, reinforcement learning, how you decide to apply reinforcement learning instead of other kind of learning, such as supervised learning or unsupervised learning. Reinforcement learning involves sequential decision making. So the important thing here is you don't have the IID property. Okay, so decisions at the specific state depend on decisions that you have taken in the past. A decision in a specific state also affects decisions that you will take in the future. You don't have the IID property anymore, as you have in supervised learning. So when you classify an image, you classify that image. Okay, you go on to the next image. This is not the case here. This is the most general rule, I would say.
Okay. Let's please thank our speaker again.